Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Interference of Light. Take down the sum please. A monochromatic light of wavelength, a monochromatic light of wavelength, a monochromatic light of wavelength 6000 Armstrong units, a monochromatic light of wavelength 6000 Armstrong unit falls normally on a slit, falls normally on a slit of width 0.1 millimeters, 0.1 millimeters. Find the singular position, find the singular position of the first secondary maximum of the first secondary maximum and the third minimum in the diffraction pattern, in the diffraction pattern. Now let's assume that theta 1 is the angular position. Let theta 1 be the angular position of the first secondary maximum. Right? Now in that case, how do you get a maxima for a diffraction pattern? A maxima for diffraction pattern is given by the formula A sin theta 1 is 2n plus 1 lambda by 2. That's the formula for your maxima, right? So I can therefore say, now since I can say this is A, since theta is very small, sin theta 1 will approximately be equal to theta 1. As theta 1 is very small, I can say that sin theta 1 is approximately equal to theta 1. Therefore, I can say A theta 1 is going to be 2 into 1 plus 1 into lambda by 2, right? Why 1? Because n, guys, since I want the first secondary maxima for first secondary maxima, n is going to be equal to 1. That's how I got this. This is a formula, right? That's a formula for maxima, straightforward. So I'll get A theta 1 is going to be 2 plus 1, 3 lambda by 2, right? Once I have this, then I can straight away say that theta 1 is 3 lambda by 2a. I have the value of lambda, I have the value of a. I'll get my answer in terms of degrees, right? So you can get your answer. This will give you, let's solve this guys, 3 lambda 6000 into 10 raised to minus 10 upon 2a, 2 into 0.1 into 10 raised to minus 3, right? Now when I solve this, I will get this answer as 9 into 10 raised to minus 3 radians. If I want to convert this into degrees, I have to convert this into degrees. The conversion factor is, this can be written as 9 into 10 raised to minus 3 upon 1.75 into 10 raised to minus 2. When you divide by 1.75 into 10 raised to minus 2, you are converting from radians to degrees. When I solve this, I will get this as 0.514 degrees. So that is going to be the angular position for the first maxima, right? So for maxima, guys, this is the formula. A sin theta 1 is 2n plus 1 lambda by 2. Next, let's see the formula for minima. They have also asked you the position for the third minima. You would say let theta 2 be the angular position of the third minima. Right, now for minima, the formula is a sine theta 2 is equal to n lambda. For maxima, that was the formula. For minima, the formula is a sine theta 2 is equal to n lambda. Right, now since this is third minima, I can say, since it is third minima, n will be equal to 3. Right, so I can there, and also as theta is very small, I can say that sine theta is approximately equal to theta. Therefore, I get a theta 2 is 3 lambda. Therefore, I can say that theta 2 is 3 lambda upon a. Right? In which case you will get this as theta 2 is 18 into 10 raised to minus 3 radians. Convert this into degrees. To convert it into degrees, I can further divide this by 1.75 into 10 raised to minus 2. 1.75 into 10 raised to minus 2 degrees. Fine. So you can solve this and get the answer. So do we understand how to get the maxima and minima for a diffraction pattern? Next, take down next one please. The second order diffraction minimum. The second order diffraction minimum of 6000 Armstrong unit the second order diffraction minimum of 6000 Armstrong units coincides with the second maximum of another wavelength. Coincides with the secondary maximum of another wavelength in a diffraction pattern. Right? Calculate the secondary wavelength or calculate the second wavelength. Now guys, here they've given you that the diffraction pattern coincides, the diffraction pattern coincides. Since the diffraction coincides, that means A sine theta 1 should be equal to A sine theta 2, right? Now A sine theta 1, where I can say where theta 1 is the angular position, where theta 1 and theta 2 are angular positions of the second minima and second maxima. Second minima and second maxima. Fine, do you get this in here? Once you have this, then I can say that now second minima and second maxima, right? So in this case, I can therefore say that minima, so that means it will be n lambda. So I can say n lambda 1 maxima is nothing but 2n plus 1 lambda by 2. A sine theta 1 for minima it is given by the formula n lambda 1, and for maxima it is 2n plus 1 lambda 2, where I can say both are second, so n will be 2. So 2 into lambda 1 is 2 into 2 plus 1 lambda by 2. So 2 lambda 1 is 4 plus 1, 5 lambda 2 by 2 You have the value of lambda 1, you can get the value of lambda 2, right? Substitute and you should be able to get that answer. The answer for this should be 4800 Armstrong units. Next, take on next one please. A monochromatic light is incident on a 0.022 millimeter width. 0.022 millimeter width, and the first diffraction minima is obtained at 1.8 degrees. Calculate the wavelength of the incident light. Right? For minima, I can say that A sin theta is going to be equal to n lambda. Right? Now, since theta is very small, straight away I can say A theta is equal to n lambda. A is given to me. I can say that I have to find out lambda. So lambda is going to be nothing but A theta upon n. A is 0.022 into 10 raised to minus 3. Theta 1.8 degrees. To convert this into radians, I'll have to multiply this by 1.75 into 10 raised to minus 2, conversion factor, upon n. N is going to be 1 because this is first minima. Substitute, you will get this answer. When you solve this, you will get this as 6930 Armstrong units. So the wavelength of light used is 6930 Armstrong units. Next, take on next one please. A monochromatic light has a wavelength of 4800 Armstrong units. A monochromatic light has a wavelength of 4800 Armstrong units. Diffraction pattern is obtained on a screen. Diffraction pattern is obtained on the screen 1.2 meters away from the slit. The second diffraction minima is found to be 0.95 centimeters from the central maxima. 0.95 centimeters from the central maxima. Calculate the angular position. And the width of the slit. Calculate the angular position and the width of the slit. Right? Let's see this. They've given you that, let's assume that AB is the slit. This is the screen. The screen is at a distance of A. I have second minima which is obtained. Let's assume that it is obtained at a distance. This distance is 0.95 95, they are saying centimeters. Second minima is obtained at 0.95 centimeters. If second minima is obtained at that distance, first let's find out the angular diffraction. Now from this diagram, this is what exactly is happening. You have light passing through a slit and the second minima is obtained at 0.95 centimeters from the central bright band. So let's first get the angular diffraction. I can easily find the angular diffraction here by using the formula tan theta. Tan theta is 0.95 into 10 raised to minus 2 upon d, converting centimeters to meter. So I'll get tan theta is 0.95 into 10 raised to minus 2 upon d. D is going to be 1.2 meters. They have directly given it to you, right? So when you solve this, you will get, now since theta is very small, I can say tan theta is approximately equal to theta. Therefore, I can say theta is going to be, when you solve this, 95 upon 21 into 10 raised to minus 1, which will come out to be 0.45 degrees. Right? When I convert this, I'll get this in terms of radians. First, I'll get the answer in terms of radians, and to convert it into degrees, I'm going to be dividing this. I'll write it in degrees only. 1.2 into 1.75 into 10 raised to minus 2. What did I do here? I converted from radians to degrees. Fine. So I'll get the answer as 0.45 degrees. So I've got the angular diffraction. Next, they've asked you to find out the width of the slit. Okay. Let's see this. Now for second minima. For minima, the formula is A theta is nothing but n lambda. That's the formula for minima. So in that case, I can say that A is n lambda upon theta, right? N, second minima, 2, lambda, wavelength of light, 4800 into 10 raised to minus 10 upon theta, 0.45. It is in degrees. Convert this back into radians. If I convert this back into radians, this will be nothing but 1.75 into 10 raised to minus 2. Simplify this, you will get the width of the slit. You will get this answer as 0.12 millimeter. Right, that's how you will get the width of the slit. Next, take on next one please. Light of wavelength. Take on next one please. Light of wavelength 6250 Armstrong units. 6250 Armstrong units is incident on a narrow slit. The angular separation between the first diffraction minima, the angular separation between the first diffraction minima on either side of the central band is 1.5 degrees. What is the width of the slit? What is the width of the slit? Right? Now guys, you have a slit here. They are saying that the angular separation between the first diffraction minima on either side. I'm going to get a diffraction minima at P and say P bar. They are saying that the angular separation between first diffraction minima on either side is 1.5 degrees. Now obviously this is going to be a symmetrical pattern. Therefore, what will be the angular separation between the central maxima and the first minima, half of it? I can therefore say that theta is going to be equal to, guys, theta is going to be nothing but 1.5.2, that is 0.75 degrees. Once I have this, then it's a very straightforward sum, right? I can say that for minima, I'm directly writing, I'm not going to write sin theta, I'm writing a theta is going to be nothing but n lambda. N is 1, so I can straight away say that a is lambda upon theta. Lambda is given to you as 6250 into 10 raised to minus 10 divided by theta. Theta is 0.75 degrees. Convert that into radians, into 1.75 into 10 raised to minus 2. For calculation, you have to make sure that your angle is in radians. Simplify this, you will get your answer as A will come out to be 0.04762 millimeters. Right? Take down next one, please. A light of wavelength 587.5 nanometers. A light of wavelength 587.5 nanometers illuminates a slit of 0.75 millimeter. Illuminates a slit of 0.75 millimeter. At what distance from the slit should the screen be located? At what distance from the slit should the screen be located if the first minima is to be at 0.85 millimeter, if the first minima is to be at 0.85 millimeter, from the central screen. Guys, let's visualize this. This is the slit, this is the screen, this is the central maxima. They are saying that the first minima is located, this is x, it is located at a distance of x. D, A, B, there is going to be a slit of some width. Now, first of all, I can say that for first minima, let's assume that this angle is theta. So in that case, I can say that A theta is n lambda, right? N is going to be 1 because this is first minima. So in which case theta is going to be lambda upon A. Lambda is 587.5 into 10 raised to minus 9 upon A. 0.75 into 10 raised to minus 3, right? So in that case, when you solve this, you will get this answer in terms of radians. You will get theta is 7.832 into 10 raised to minus 3 minus 4 radians, right? Once I have this, then I can convert this into degrees. This can be written as, I have this in radians, so I can say that for calculations as it is, I need it in radians. I can use the formula tan theta is x upon d. Since theta is very small, therefore I can say tan theta is going to be equal to theta. Theta is x upon d. Therefore I can say that d is x upon theta. X you have found out as 0.85 into 10 raised to minus 3 upon theta 7.832 into 10 raised to minus 4, right? So in which case you will get this as When you simplify this, you will get this as 1.085 meters. So the screen has to be at a distance of 1.085 meters, right? Next, they have also asked you the width of the central maxima. What is the width of the central maxima? Now guys, we haven't done this formula, please see this. The width of the central maxima W is given by the formula 2d lambda upon A. That's the formula for width of the central maxima. Fine. You have all the values. You have D, you've just found out. Lambda you have, A you have. You should be able to get this answer. The answer for this should be 1.7 meters. Next, take on next one, please. A screen is placed 50 centimeters. A screen is placed 50 centimeters from a slit which is illuminated by a light of 690 nanometers. If the distance between the first and the third minima is 3 millimeters, find the width of the slit. Right? Let's assume that point P, point Q and O is the central maxima. Let's assume point P is my first minima and has an angular position of θ1. Point Q is my third minima and its angular diffraction is say θ2. Right? Let's assume that this distance is x1 and this distance is x2. What they have given me is they have given me the distance between the first minima and the third minima. That means they have given me length PQ. Okay. Now let's try to solve this. First of all, I can say that for first minima n will be equal to 1. For first minima n will be 1. So I can therefore say that distance of first minima x1 is given by the formula A sin θ1, we've already done this, which is equal to n lambda, right? So n is 1, so in which case I can therefore say that A θ1, we've already been doing this, A θ1 is equal to n lambda, therefore I'll get θ1, n is 1, so there will be lambda upon A. So I'll get the angular diffraction for the first minima. Same way I can get the angular diffraction for the third minima. I can say that for third minima I can say that A θ2 is equal to n lambda, where n is going to be equal to 3. So I'll get θ2 is 3 lambda upon A, right? So that is going to be my angular diffraction there. Now I can say that, let's consider, I'll just draw this diagram again here. Central bright band, first minima, third minima. This angle is θ1, this angle is θ2, this was O, P and Q, and let's call this point as C. Okay, we found out the value of θ1 and θ2. Now in triangle TOC, I can say that tan theta 1, tan is nothing but OP upon OC. Tan is nothing but opposite upon adjacent. But since theta 1 is very small, therefore theta 1, OP is nothing but x1. We had assumed this distance to be x1 and we had assumed this distance to be x2, right? x1 upon, this is the distance between the slit and the screen. Therefore I can say that theta 1 is equal to x1 upon d, right? But we have already found out that theta 1 is nothing but lambda upon a, right? But theta 1 is lambda upon a, therefore I can say lambda upon a is x1 upon d, right? Therefore I can say that x1 is lambda d by a, cross multiplying. Same way I can say in triangle QOC, I can say that tan theta 2 is going to be nothing but OQ upon OC. Tan theta 2 is going to be nothing but OQ upon OC. Since theta 2 is very small, therefore theta 2 is OQ x2 upon OC d. But we have found out that theta 2 is 3 lambda by a, therefore I can say that 3 lambda by a is x2 upon d, therefore I can say x2 is 3 lambda d by a, right? But what is x? But x is nothing but x2 minus x1. X is the distance between the third dark band and the first dark band, right? So in that case I can therefore say that x is equal to x2 3 lambda d by a minus x1 lambda d by a, therefore I can say x is equal to 2 lambda d by a, right? 3 lambda d by a, out of which I know the value of x. They have given you that the distance is 3 millimeters, so 3 into 10 raised to minus 3. 2 lambda is given to you as 690 into 10 raised to minus 9. D is given to you as 50 into 10 raised to minus 2 divided by A. Right? A is now given to you, the width of the slit. Therefore, I can say this is going to be 2 into 690 10 raised to 9 minus 9 into 50 into 10 raised to minus 2 upon 3 into 10 raised to minus 3 will give you A. That's how you will get the width of the slit. Right? Next, let's see the next sum, guys. Calculate the limit of resolution. Calculate the limit of resolution and the resolving power. Calculate the limit of resolution and the resolving power of a 0.15 meter diameter, 0.15 meter diameter telescope at a wavelength of 5,900 Armstrong unit. At a wavelength of 5,900 Armstrong unit. Now, I can say for a telescope, the limit of resolution d theta is given by the formula 1.22 lambda upon d diameter. That's the formula for limit of resolution of a telescope. You know lambda, you know d, you should be able to get the answer. Right? Do we get this thing here? Next, the next part is the resolving power. The resolving power is the reciprocal of limit of resolution d theta You already found out d theta. You can, reciprocate it and get that answer. So you will get this answer. The answer for this should be d theta is going to be 4.8 microradians, and resolving power is going to be equal to 2.083 into 10 raised to 5. That is going to be the resolving power, right? Okay, we'll stop this here for the day. Thank you very much.